Hello and welcome to Chapter 2, Earth's Physical Systems, Matter, Energy, and Geology. In Chapter 2, there are some pretty general themes from biology and chemistry, which I'm not going to go into in such great depths. And so before I go to those topics, I'm going to let you know, and I can refer you to more detailed videos on our website, but I'm just kind of going to briefly jump over those topics. Okay. Matter and chemistry. So matter is all materials that have mass and that occupy space, either solid, gas, or liquid. And chemistry is imperative to environmental science for a couple of reasons. On topics such as air pollution and wastewater treatment, chemistry directly ties to environmental science. Okay, matter is conserved. Okay, so the law of conservation of matter. Basically what this says is that matter can be transformed from one substance into others, but it cannot be created or destroyed. So in environmental science, if you look down at this diagram here, in nutrient systems, matter is constantly recycled from the soil to other nutrients and around the entire ecosystem. And even though it changes states and forms, the amount of matter remains the same. Okay, so here's where we're going to start getting into the basic chemistry. And so I'm just going to briefly jump over many of the topics addressed in the book, but if you want more detail, I am going to refer you to the chemistry videos on the website. Okay, so atoms and elements are chemical building blocks. Okay, so atoms. Atoms are the smallest units that maintain chemical properties of the element. Atoms are made up of protons, electrons, and neutrons. Okay, isotopes. Isotopes are atoms of the same element with a different number of neutrons. And some of these isotopes are radioactive, meaning that they decay and release high-energy radiation until they are no longer radioactive. Half-life is a concept that refers to isotopes and other radioactive substances. And a half-life is basically the amount of time it takes for half of the said radioactive substance to undergo decay. Okay, ions. Ions are electrically charged atoms, and this happens from either the gain or the loss of an electron, or electrons, as you can see in this diagram here. Okay, molecules, pH, organic and inorganic compounds. So again here, I'm going to relay you to both biology and chemistry videos so that you can get a more detailed explanation if you need the extra help. But really these are pretty general topics, so I think this should be okay. Okay, so molecules. A molecule is the combination of two or more atoms. In APES, the common molecules that you really should be familiar with are CH4, methane, and O3, ozone. These are going to come up a lot in later chapters of the book. Okay, the pH scale. The pH scale numbers 1 through 14. Numbers 1 through 7 are acidic solutions, and number 8 through 14 are basic solutions. Okay, organic compounds. Organic compounds are atoms of carbon and hydrogen joined by bonds, which may also include nitrogen, oxygen, sulfur, and phosphorus. Great. A polymer are made up of organic compounds, and so a polymer is basically a long train of monomers, which forms one large molecule. So if you put a bunch of these carbon, hydrogens, and nitrogen, oxygen, sulfur, and phosphorus together, you can end up with a polymer. Okay, a hydrocarbon is a bond of only hydrogen and carbon. And so basically we derive most of the fossil fuels from hydrocarbons. So oil, coal, all of those. Okay, plastics. So a plastic is a synthetic polymer. We're all pretty familiar with plastics. You can look down here. Any plastic bottle, anything really. And so these synthetic polymers, plastic, are derived from hydrocarbons in petroleum. So basically, plastics are very dangerous to the environment for the reason that if they're not recycled like they should be, then they go to a landfill, which is where most of the organic waste goes. But as you can see, because they're synthetic polymers, plastics don't biodegrade in the same manner that organic matter does, and so it doesn't really work. So they just sit in the landfills and they don't biodegrade, and it's really, really bad. So you need to either recycle plastics or just even better yet, don't use plastics. Okay, energy. So energy is basically connected to every aspect of our lives. The main source of energy that we're familiar with would be down here, this guy, the sun. Okay, so let's explain the difference between potential and kinetic energy. Okay, so potential energy is the energy possessed by an object by virtue of its position or state, versus kinetic energy, which is the energy possessed by an object by virtue of its movement relative to other objects. Okay, and down here, the first and second law of thermodynamics, photosynthesis, and cellular respiration, those are pretty general biology topics, so I'm going to refer you for more detail other than the book to our biology videos on those, just to save some time. And they're not that directly important to what we're talking about right now in environmental science. Okay, Earth's layers. So you can refer to the diagram while I explain this. Okay, so starting in here at the core, the inner and outer core. And granted, this is a pretty generic model of the Earth's layers, but it helps get the point across. Okay, so down here in the core. So the core is mostly made up of molten iron. And as we move out, the mantle, which is this bit here, is made up of mostly elastic rock, and it gets less dense than the core. And then out here, the lithosphere, consists of the crust, which is the layer that we live on and that we're most familiar with. So that's basically like a general breakdown of like the layers of Earth. Also, we can use geothermal heat pumps to collect this energy. And so when we refer to geothermal heat energy, we're referring to taking the energy from the inner layers of the Earth. Okay, plate tectonics. Although plate tectonics doesn't seem like it would be that important of a topic to make sure you really understand, believe it or not, one of the free response questions on the AP this past year was on plate tectonics, even though it's in chapter 2. So you have to make sure you know this stuff actually throughout the year. Okay, so plate tectonics refers to the movement of lithospheric plates. And as you can see down here, the Earth consists of mainly 15 major plates that kind of jigsaw together. Okay, so plate boundaries. Okay, there are three main types of plate boundaries: divergent, transform, and convergent plate boundaries. Okay, so divergent boundaries. Divergent boundaries push apart one another in a magma state, rising up and creating a new layer of lithosphere. Okay. Transform boundaries consist of two plates grinding together, causing an earthquake along fault lines. And convergent boundaries can experience two different outcomes. First, subduction can occur. This consists of cooled magma sinking down, then this same magma heats back up and could cause a volcanic eruption when it's pushed back to the surface. Second, a continental collision could occur, which is what basically forms mountain ranges. Okay, the rock cycle. Okay, we're all pretty familiar with the rock cycle. We've gone over this in many science courses before, environmental science, but just a quick run through. You can look at the diagram here. So basically, we can start at sedimentary rock. So basically, sedimentary rock is changed by heat, pressure, and or chemical action into metamorphic rock. From there, metamorphic rock is melted into magma. The magma solidifies, forming igneous rock, and then from there, the igneous rock can weather and erode, reforming sedimentary rock. So it basically just runs through the continual cycle. Okay, so effects of earthquakes, volcanoes, and landslides. So when you're looking at the effects of all three of these major disasters, you can refer to the immediate damage that one would follow. So like an earthquake, like damaging buildings and things. That's what I'm referring to in that sense. However, another effect that could happen is when a volcano erupts, like a black soot almost could cover the sky, blocking sunlight. And when this happens, that could stop photosynthesis and other natural systems, which is really, really bad. Also, at any point, all of these three different environmental occurrences could displace a huge volume of water and lead to a tsunami along a coastal area. Any three of them have the capacity to start this. Okay, how we worsen these natural hazards. So although they are referred to as natural disasters, it's pretty clear that there's a connection between human interaction and the worsening of said disasters. So mainly population increase. As there are more people, all of these things subsequently happen, so we're burning more fossil fuels, etc. Moreover, this growing population lives in what we refer to as desirable areas, so along a coastline, for example. So if you refer to California in this sense, California is highly susceptible to earthquakes, and because it's on the coast, tsunamis, obviously. And even though these things definitely occur here, people still want to live along coasts, which could lead to more damage. Also, the damming of rivers, suppressing of natural fires, and mining also could worsen these natural disasters. They're all theories. And obviously, emitting greenhouse gases, as down here, this factory burning what looks like coal, harms the environment and could worsen these environmental factors. Okay, so in conclusion, there seems to be a clear link between chemistry, biology, and environmental science. Moreover, there is a connection between our environmental impact on the world and natural disasters. Next chapter, we're going to look into evolution, biodiversity, and population ecology.